Hi dears, hope you all are sound and safe. Today we can discuss the topic the waves in one dimension. Under the topic we have to study the wave equation and sinusoidal waves and the boundary conditions regarding transmission and propagation of waves. And the first topic is wave equation. Do you remember what is a wave? A wave is a disturbance of a continuous medium that propagates with a fixed shape at a constant velocity. That is, a wave is a disturbance of a continuous medium that propagates with a fixed shape at a constant velocity. Hope you have heard this and also about the wave equation in your previous studies. And can you explain what is a standing wave? It does not propagate at all. And also, in case of a 2 or 3 dimensions, the waves spread out and its amplitude decreases. For the explaining our current theories, we can consider a wave which have a fixed shape and a constant velocity. We can start with the topic wave equation. To explain wave equation, first we can consider a long string which is held with a tension T. And consider the string is coinciding with the x-axis of the coordinate system. Now, the string is along the x-axis. Now, I am going to plug the string along y direction. Plug the string along y direction. Then the string will be having a transverse motion along y direction. That is, I can represent the initial position of the string as like this. We are considering long string which is held by a tension T, and I am plucking it is coinciding with the x-axis, and I am plucking a portion along the y direction, and it will be having a transverse motion along y direction. Now I am going to consider a segment along this string, and I am going to name it as x and it as x prime. So, the tension at this point will be along this direction, and the tension at this point will be along this direction. Both are the same tension T in opposite direction. Here the tension is leftward direction, and here the tension is along rightward direction. Now, I can represent the angle of tension. That is, the tension T at point x with the x-axis is considered as theta. The tension T at x is making an angle theta with the x-axis. And we can resolve this tension like this. And this component will be T sin theta, and this component will be T cos theta. And T cos theta is along negative x direction, T sin theta is along negative y direction. Similarly, in this case, the tension is along rightward direction, and the angle which the tension at x prime makes with the x-axis is given as theta prime. And we can resolve these into these directions, and this will be T cos theta prime, and this will be T sin theta prime. So, the T cos theta and T cos theta prime will be the components along x direction, and T sin theta and T sin theta prime will be along the y direction. Now, the string is stretched strictly along the x direction, and we are producing a transverse force along the y direction. So, we have to derive the displacement along the y direction only. So, we need to consider these two resolved components, that is T sin theta and T sin theta prime. Here, this point is considered as x, and this point is considered as x prime. And also we can write x prime is equal to x plus delta x. Practically, these two points are so nearby points. Now, the displacement of the string due to the transverse wave can be written as y is equal to f of xt as the wave is traveling along x direction or stretched along x direction. So, the resultant transverse force acting on the segment which we consider can be written as f is equal to t sin theta prime minus t sin theta, that is this force segment. That is t into sin theta prime minus sin theta. Here we know theta is the angle made by the t with the x-axis and theta prime is the angle made by t at x prime with the x-axis. Now the displacement of the string is very small along the y direction as the string is strictly stretched along x direction. So theta and theta prime will be very small angles. In such a case, we can equate sin theta as tan theta and sin theta prime as tan theta. So the resultant transverse force can be written as F is equal to T into tan theta prime minus tan theta and give it as equation number 1. Simply we know tan theta is the slope at the point x and tan theta prime is the slope at the position x prime. And we know the slope can be written as tan theta is equal to dou y by dou x or dou f by dou x where y is equal to f of xt. Now we can substitute this equation 2 in equation 1. Substituting 2 in 1, we can write f is equal to t into dou f by dou x at x prime, that is x plus delta x minus dou f by dou x at x, that is equation 3. And we know mathematically dou f by dou x at x plus delta x can be expanded as dou f by dou x at x plus dou by dou x of dou f by dou x into delta x, that is dou f by dou x at x plus dou square f by dou x square into delta x. This is equation number 4. Now I am going to substitute this equation 4 in 3. 4 in 3, that is f is equal to t into dou f by dou x at x plus dou square f by dou x square into del x minus of dou f by dou x into at x. In this equation, these two terms will be cancelled and only the remaining will be t into dou square f by dou x square into del x. That is f is equal to t into dou square f by dou x square into del x, which is given as equation number 5. Now we can explain the same system with the help of Newton's second law of motion, which is equal to the force is equal to mass into acceleration. In this, if m represents the mass per unit length of this stretched string and also we are considering the same segment between x and x prime, that is x and x plus delta x, the force will be m delta x into acceleration, that is dou square f by dou t square. Here mass per unit length is m and total mass is m into delta x for the segment delta x. M delta x into dou square f by dou t square, which is given as equation number 6. By comparing these two equations 5 and 6, I am going to write it as t dou square f by dou x square into del x is equal to m del x into dou square f by dou t square. As the del x is common on the LHS and RHS, this equation will be dou square f by dou x square is equal to m by t dou square f by dou t square, which is equation 7. Now we know the one-dimensional wave equation dou square psi by dou x square is equal to 1 by v square dou square psi by dou t square, where psi is the function which represents the wave, and it is equation number 8. By comparing these two equations, we can write 1 by v square is equal to m by t, that is this, which implies v is equal to root of t by m. T is the tension applied and m is the the mass per unit length of the string and v is the constant velocity with which the string moves. And this equation is known as classical one-dimensional wave equation. Classical one-dimensional wave equation. From these equations, we can represent a wave as f is equal to g of x plus or minus vt, where one portion travels along the positive direction and the another along the negative direction. Here we can write the solution f of xt as g of x minus vt plus h of x plus vt, where this represents the positive component and this represents the negative component. That is, this is traveling along the positive direction and this is along the negative x direction. Thank you.